Weather, one of the most astonishing forces on Earth, capable of both devastating power and spectacular beauty. Wherever you live on the planet, weather shapes your world. Yet for most of us, how it works is a mystery. To really understand weather, you have to get inside it. So I'm going to strip weather back to basics.
All in the name of science.
Uncovering its secrets in a series of brave, ambitious, and sometimes just plain unlikely experiments.
Well, it certainly feels like a dust storm from here.
To show you weather like you've never seen it before. There is a powerful, invisible force that moves around us, almost unnoticed. A force that drives almost all the extreme weather on our planet. That force is wind. In this program, I'll discover how wind creates that extreme weather, what it's capable of, and just how fast it can go. Along the way, I'll attempt to measure the speed of a tornado right next to the ground.
Oh, that's huge.
I'll create a whirlwind made of fire to discover how a wind becomes a spinning wind. And I'll become one of the few people in history to deliberately walk into the middle of a twister.
I'm going in.
This is said to be the place with the worst weather in the world. A place so forbidding that only the fearless or the foolhardy would want to experience it. So, hazard a guess where we're starting. This is Mount Washington, in the unlikely location of New Hampshire, USA. You wouldn't expect extreme weather to be found in New England. But on April 12, 1934, Mount Washington Weather Station measured one of the fastest wind speeds ever recorded on land. 231 miles an hour. In fact, winds here hit hurricane force more than 100 days a year. Now, bear that in mind during the next couple of minutes. Because I'm about to take a little walk outside.
Okay, just popping out, which is, it turns out, quite a chore out here. I can not only hear the wind around this building, I can feel it. The whole place is vibrating. Oh no, I've forgotten my goggles. This is doing it in the wrong order, and you just, right, your eyeballs can freeze. Any exposed skin, you have frostbite on it within 2 or 3 minutes. Right, that's my best hat. I won't get cold with that on. This is to stop my nose falling off, which would be bad because I'd never be able to wear sunglasses again when I want to. Liner gloves. Mittens. Okay. Obviously, I am now obliged by law to say I'm going outside. I might be some time. I mean, that's how cold it is indoors.
At this point, I think I should try and give you some idea of what I might be in for, with a small demonstration. The lightest wind you can feel on your face is about 5 miles an hour. Enough to rustle this newspaper. 15 miles an hour, and your umbrella gives up the ghost. 25 miles an hour can cause a deck chair to set sail. Followed at 30 miles an hour by your garden furniture. 45, and all hell starts to break loose. Seemingly rigid structures suddenly make a break for it. And at 55 miles an hour, even small buildings are on the move. So why am I telling you all this? Because on Mount Washington, it's currently 65, with gusts reaching a staggering 85 miles an hour.
Believe it or not, I'm actually sheltered at the moment. There's hardly any wind right here because I'm in the lee of the building. It starts about 6 feet that way, and then there's a lot of it. And the only way to demonstrate that is I'm gonna go and stand in it. And for reasons best known to themselves, Brendan and Sean on camera and sound have decided to come with me because they're idiots. So, here we go. Right, walking, not windy, not windy, not windy, oh, getting windy, getting windy. Hey, this is about 65, maybe 70 miles an hour worth of wind. But don't forget, this is the site of one of the highest wind speeds ever recorded by man, 231 miles an hour. How must that feel? I'd be gone. They do a calculation around these parts where you take your weight in pounds. I don't know what I am, it's about 150, 160. Halve it, that's the wind speed at which you're going to get into trouble, which is about this wind speed. There are 3 major storm systems that meet right here. Sort of long distance weather patterns. And that corner behind me is the most exposed place, which should make that the windiest spot on this whole mountain.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen. All for free. No subscription required.
But lots of places have storm systems. Why is it here that's so windy?
Don't worry about this. They said it was just a precaution. So, take my hat, the one that caused this in the first place. Let's pretend this is Mount Washington. This desk fan is the wind. And we can see the wind hitting the top of the mountain. Mount Washington is the highest thing for miles around. So although there are hills here and a town here, ski resort there, they make no difference to the wind hitting Mount Washington. They're not high enough as obstacles to block it or disrupt its flow, so any wind there is will hit the top of the mountain. But there is another reason why it's so windy up there, and it's complicated enough to demand a clipboard. All of our weather happens in the troposphere, the first 11 miles or so of our atmosphere, and the top of that layer acts as a sort of ceiling. You know what it's like when you squeeze the end of a garden hose and the water comes out more powerfully, more quickly, because it's squeezed through a narrower gap? It's exactly the same here. Use this. It's a precaution. The wind is forced through the gap between the top of the mountain and the top of the troposphere. That's a narrower gap, so it speeds up. And that's why
It always tends to be windy at the top of a hill. So wind is just air rushing from one place to another, speeding up as it goes through narrow gaps, slowing down as it hits obstacles. There are winds near the ground that blow locally, and ones high in the air that can blow long distances. And that is information you can use to your advantage.
Right, here's how to amaze your friends. First, stand with the wind at your back. Then you're looking for clouds. If those clouds are moving overhead, directly away from you, or directly towards you, or they're stationary, then the weather is going to stay broadly the same. If they're moving from left to right, it's going to get worse. If they're moving from right to left, it's going to improve.
So, right to left, better. Left to right, worse. Straight down the middle, stays the same. As long as you have your back to the wind.
Unless you're in the southern hemisphere, in which case you reverse that bit. Brilliant, isn't it? Really clever. I mean, it's not 100% foolproof because weather's really complicated, but it works more often than not. And that's about as much as you can say of any form of weather forecasting, isn't it?
And the clouds must have been travelling right to left up on Mount Washington. Because the next morning is truly spectacular. Unusually for this time of year, the cloud lifts and the wind subsides. Slightly. And I venture back outside into a suddenly magical landscape.
Folks around here quite proudly proclaim that it has the worst weather in the world. And, well, I don't know. I mean, severe, yes, but looking at it like this, worst, not so sure.
But there's no doubt that this is a place shaped by wind. It's so windy here that the buildings have to be chained down. Even the ice appears to fly off in frozen streamers. These streamers don't point away from the wind. They grow towards it, and here's how. Ice crystals are carried through the air by the wind. But the moment they touch an object, they freeze tight. The next ice crystal to be blown in freezes to the first. gradually building outwards in the direction they blew in from. And that gives me an idea.
I've thought of another way you can see wind. I looked around and a lot of the snow that I can see in the air isn't falling, it's been blown by the wind, sticking to any available surface. So, I've got a pocket full of this biodegradable confetti. Let's wait for a good gust.
Watch how the confetti blows in swirling patterns. You'd think that at these wind speeds everything would just get whisked away in a perfectly straight line, but it doesn't. It rolls and curls like waves crashing onto a beach, and occasionally those rolling eddies turn into tightly knit spirals in a shape scientists call a vortex. It's a shape that's crucial to our story, because almost all the weather we think of as extreme is based around them. This isn't just about strong winds, it's about the other types of weather that wind can produce. Dust devils, water spouts, tornadoes, all are spinning winds based on this vortex pattern. Even hurricanes and cyclones have the same spiral shape. But to see how those spirals come about, I'm going to examine perhaps the most unusual vortex of them all. It's called a firewhirl. And because they're made entirely of flames, it's easier to see the twisting structure. Right here is where I'm most likely to find one. The tinder-dry forests of Western Australia. The vegetation here is so flammable that any stray match or lightning strike can have it ablaze in seconds. There are 50,000 bushfires a year in Australia, and almost any one of them is capable of creating a firewhirl. But because the fires are so impenetrable, and because firewhirls tend to be so short-lived, it's very rare to actually see one. Which is why the best way to examine a firewhirl is to build one.
But I'm not going to set about building a firewhirl on my own, which is why I brought two of the world's leading authorities on firewhirls over from Japan to help.
Dr. Kazunori Kawana and engineer Kozo Sekimoto have spent many years looking at how and why firewhirls spin. And they've agreed to lend us a hand to try and start our very own firewhirl.
But I've just discovered this is the first time they've built a full-scale one, which is a worry.
Especially when I see them messing about with baking tins. Of course, we have the fire authorities on hand. But at the moment, they look like they're just there to help with the washing up. Time to find out what's going on.
Chaps, baking tins.
I'm intrigued. How does this work?
We are trying to create a firewall on top of the baking pans. We put heptane, a combustible liquid, in the pans.
Heptane, is that what that is?
Well, this is water.
You know that doesn't burn, don't you, at all?
we put heptane on top of the water layer.
I knew that. Okay, why are they arranged in this L configuration?
If the shape of fire is entirely symmetric, the swirling motion wouldn't occur. So we need some kind of trigger to create a swirling motion.
This shape, this asymmetry, somehow triggers something that we're going to see.
Exactly. Yes.
Good. Will it ultimately get rid of these flies? Because I see why you're wearing these nets. I thought you were beekeepers when I arrived, but it's unimaginably unpleasant.
But this isn't merely an extreme type of pest control. We're going to see if these 30 baking tins can help us create a spinning vortex.
And we're not just going to be looking for this vortex effect here. We're also going to be looking from up there.
We need a bird's eye view if we're going to reveal what makes a wind spin. And this remote-controlled copter is the perfect way to get it.
That is why I've brought that guy.
That guy is the drone's pilot, Hai Tran. A man with 25 years' experience of flying remote cameras. I pop over to brief him on what we're after.
Right, so if we get a firewall going out there, this spinning vortex, I need a shot directly over the top of it. As it forms, you there looking down will get the circle just there like that.
Right, so you want me to fly over a tornado that's breathing fire?
You've used very emotive language there. I mean, essentially, yes.
Okay.
I mean, yes.
Yeah, I think we're going to have problems there with all the wind and the heat that's coming off the fire. I think carbon fibre is pretty durable, but the propellers are plastic, so they'll probably melt off at some stage.
So how will you know if that starts happening? It'll warn you. Because presumably, I mean, if you get closer and you hit the wind, you'll see it go all jiggly and you can go higher.
No, these things are stabilised. So the first thing we'll see is the copter heading towards the fire.
So the stabiliser will cancel out any effects of the heat until it melts?
Yes.
Turn the stabiliser off? well, go in raw.
Yeah, okay.
You can tell your friends, no stabiliser, and I flew it into the fiery tornado thing.
I mean, we're talking about 160 kilometre winds? Yeah. No.
I try to explain to Hai why fire is important to this whole story. Because heat can create winds. Let me demonstrate with this cooker. Now, imagine the hobs represent the earth being heated up by the sun. Hot air rises off the hob just as it does from the hot ground, making the air above the flames less dense, and therefore lower pressure. But the cold air around the oven is still at normal pressure, so it rushes in to fill the gap, turning these children's windmills. And we can prove that the air is rushing towards the flames with the smoke from this match. Higher pressure air rushing towards lower pressure air. That is the basis of wind. Using flames only accentuates the effect, which is why a massive fire is the best way to create our own extreme wind. But it still doesn't tell us how that extreme wind can start spinning. That is why we need the drone. So, here's the plan. First, we get a flammable liquid called heptane and fill the pans with it. Once they're all full, we'll set light to them. If Kazu and Kozo are right, their L-shape arrangement will spontaneously trigger a firewhirl. Next, we'll introduce some coloured smoke to see if our eye in the sky can capture the wind patterns at work. Right, let's give it a go. Time to stand well back. At first, it all seems a bit underwhelming. It looks, well, it looks like 30 baking tins on fire. But as cold air rushes in, it feeds the flames. And then, quite suddenly, they begin to spin.
There it is.
The spin seems to intensify the fire even more. The flames grow higher and higher until they tower above us.
It's massive.
A real-life fire whirlwind. And it seems that Hai is prepared to give it a go after all.
I'm in 20.
Roger that.
If he can get close enough, then we've a chance of seeing how a fire whirl actually works.
There's turbulence up there.
Yeah, roger that.
Remember, they have no way of seeing that turbulence.
I think we're getting a bit close to the fire, Sam.
He won't know he's in trouble until the controls stop responding and the copter literally melts out of the air.
That's looking great, mate.
Okay, so now for the tricky bit, trying to see how our fire whirlwind was formed.
Just like we did with the cooker, we're going to introduce some smoke. The crosswind is so strong that the smoke stays close to the ground, and on the far side, it blows in a pretty straight line. But on this side, parts of it bend round the L shape and get sucked in towards it.
Let me try and explain what's happening here. Here's our L. And when the wind comes from this direction, it rolls around the end of it here, and it's drawn towards this fire. But it's also drawn towards this one here, and that sets it spinning. That starts our vortex. The vortex rolls along the long arm of the L, and when it gets to the fire here, it intensifies. And this is where our fire whirl is formed.
The cold air carrying the smoke on the inside of the L is being pulled in two directions at once. And it's that that creates those little spinning swirls of green smoke. And ultimately, the fire whirl our team managed to successfully capture on camera. Now, obviously, you don't generally find baking pans in the wild, but natural L's occur when two separate fire fronts meet, each creating their own opposing winds. And that's also pretty much how other types of spinning weather start. Two or more winds meeting at different angles and speeds. Some rising warm air and cold air rushing in to fill the gap. Just those simple ingredients can produce some of the most extreme forms of weather we have, including the most powerful and deadly wind of them all, the tornado. Because a tornado is spinning, it can move far faster than a normal wind. Not in a straight line, but in the speed that they can spin. And it's that spin that does the damage.
Look at it this way. If I'm spinning this bucket around my head, it's not how fast I'm walking towards you that dictates how hard it will hit you when I get there. Even if I walk really quickly, that speed's irrelevant. It's how fast I'm spinning the bucket that matters, and what's in it to add to the weight. And that's how it is with a tornado. Debris does most of the damage. That's the weight in the bucket. The most destructive force in the tornado itself is its spin, its rotational speed. Which is why it's remarkable. That's the part of a tornado we know the least about.
I'd like to find out why. And who better to ask than the Center for Severe Weather Research in Boulder, Colorado. I make an appointment with its president, Josh Werman, to ask him why that spin speed is still such a mystery.
Scientists have gotten very good at measuring the winds above the ground in the tornado, maybe from 50 meters above the ground up to a couple kilometers. But the strongest winds in the tornado are below that. We think the strongest winds in the tornado might even be below 10 meters. Using remote sensing with radars, we can get up close, we can scan back and forth, but unfortunately, objects block us. There's debris, pieces of houses, cows, whatever, flying around in the tornado, and that's the one place where we are the most blind.
Why isn't there just a machine that you can point at a tornado and measure it? I mean, it is moving past. Why can't you just measure it?
There are two main challenges with in situ measurements. The first is how to get something inside the tornado. The tornado is moving down the fields, and we don't know exactly how it's going. It's an unpredictable path. So getting something in front is very, very hard. Challenge number two is what happens when we succeed, and that is the tornado runs over the object and destroys it. So unfortunately, the place that we most need to know about is the place that's hardest for us to see. If we can understand that better, then engineers will be able to build better buildings, we'll be able to have better shelters, and fewer people will get injured and die in tornadoes.
But how would you begin to measure the speed of a tornado right next to the ground? To try and find that out, we must travel another 1,300 miles to the distinctly un-tornado-like landscape of London, Ontario. And one remarkable building.
I'm going to do something a person wouldn't normally do. I'm going in. Listen. Oh! it. I'm in the eye of it. And all I can say is, yes, this feels as amazing as I suspect it looks. I'm in a tornado. It's the most astonishing feeling. It's dizzying. The world is roaring past and spinning round me, but I'm still. This is massively scaled down, of course. A real one would be maybe 100 times bigger and the wind moving 4 or 5 times faster, but nevertheless, you get a sense of the relentless, terrifying power of one of these things in the wild. That is the most daunting sight. I've got goosebumps, and not just because it's cold in here. I can feel the edges of it, feel it moving. It's like I'm touching its flanks. It is a living, breathing thing. It's a living, breathing, furious thing.
This is the Wind Engineering, Energy and Environment Research Institute, or WINDY for short. And it's the only place on the planet capable of duplicating the real-life dynamics of a tornado. It does it by using 106 giant fans hidden behind the walls and ceiling of the world's first hexagonal wind tunnel. The whole structure cost $23 million. And it isn't even officially open yet. We're pretty much the first visitors to set foot inside. Which makes it all the more delicate asking its boss, Professor Horia Hangen, for a little favour. Just while we're here, in this facility, I'd really like to just have a little look at velocities sort of that way, in tornadoes. Can we have a... I'm not going to say it's experiment a bit with it. Do you mind if we make a bit of a mess? Not a massive mess. There might be... We'll sweep up. You won't know we've been here. Everything will be gone.
That's fine. We can do a little bit of a mess here, so we are prepared to catch some stuff that you'll throw into it. So
Might happen. Thank you.
you're welcome.
Good for him. He's trusting us with his $23 million baby.
Right, plan. They really have let me experiment with this incredible installation, and I want to look more into velocity, see how fast the wind is moving. And if I introduce these ping pong balls into our tornado, I can measure the speed. I'm going to feed them to it.
We think of tornadoes as sucking up everything in their path. Turns out it's not that easy. I retreat to the control room, where the professor and I spend the next 4 hours trying to get something, anything, to actually fly inside the tornado. With no luck. And then I think of the confetti on Mount Washington. What we need is something flat and light. We find these pink foam squares. They're similar to the confetti, but because they're substantially bigger, it should be easier to track their progress. If we can get those foam squares trapped in the tornado, and if we can get them lifted up and spun round without being spat out, then we might be able to time how long it takes one to do a full lap. That is a lot of ifs
I know, but fingers crossed.
We're gonna start the fans.
You see? There it is.
Looking good.
Yeah, yeah. That's fantastic. There it is. That's exactly what we wanted. So they're held in. Okay, now we've got the foam squares circling successfully, it's time to turn on the tracking technology. The computer follows individual squares, one after another, so it can create an average speed from the different trajectories. And it works. According to the computer, it's spinning at a shade over 22 miles an hour. The first time one has ever been measured this near the ground. Now, obviously, a real tornado is about 100 times bigger and much, much faster. But now we know we can fly things in a fake tornado.
It stands to reason we can get them to fly inside a real one. Problem is, how are we going to get them in there? I'm not standing next to it with a bucket. I have tried some things. None of them really worked. I need help with this.
So I've made contact with a scientist who says he might have a solution. He's asked me to meet him here in, well, as it turns out, the middle of nowhere. This bizarre vehicle is the Dominator 3, a hand-built tornado-proof armoured car. And as meteorologist Reed Timmer explains, it's one of a kind.
There's no other vehicle like this. It's just one big meteorological instrument. It's like a mobile tornado probe.
Has it ever been in the base of a tornado?
This has. This is the Dominator 3, so this is brand new last year, and we intercepted 3 or 4 tornadoes.
What happened to Dominators 1 and 2? Gone?
Oh, no, they're still on the ground, thankfully.
What I want to know is, what are the chances of using the Dominator to measure the speed of a tornado near the ground?
Near the base of the tornado is one of the biggest mysteries of tornado science, and it's also the most important to understand because it's those wind speeds that directly impact the structures and cause the destruction that we see with tornadoes every spring and summer. That's why we built this vehicle, is to get up close and not inside those and unravel those mysteries.
So if you could get this into a tornado, you could deploy something into it that will allow you physically to measure that rotational wind speed. It is roughly what I was doing with bits of foam in the indoor artificial tornado. It's just with the real one. Yeah. It is presumably then quite incredibly dangerous.
Yeah, there is a level of risk involved, but as a storm chaser, all I've done since I was 18 years old is get close to tornadoes.
Which really begs just one question.
Are you a scientist, an adrenaline junkie, or a lunatic?
Probably all of the above.
Okay.
Reed sounds like the perfect person for us. Using the Dominator, he can get really close to a tornado, and he's already thought about how he could fire a data recording probe right into it.
So I wanted to stop right here.
Yeah.
Because just south of our position, right down there, was a F5 tornado back in 1999, and they recorded the strongest wind speeds ever recorded on the planet, over 300 miles an hour right down here just to our south.
In less than 21 hours, 74 tornadoes touched down in the states of Oklahoma and Kansas. The most prolific outbreak in history. But the most destructive of them all was right here. In the 60 minutes or so of its existence, its phenomenal spin speed caused more than $1 billion worth of damage. Scientists measured the winds inside it at 300 miles an hour. But those speeds don't tell the whole story.
Those winds were measured higher up above the ground, and who knows how strong those wind speeds were right near the Earth's surface with the strongest tornado in history.
And that came through right where we are?
Yeah.
So, if this were a real situation, what do you say, hot, live, whatever. If it were coming towards us, and you're here with this, what happens now?
Well, we'll look to the southwest. If it's not moving side to side at all, it's likely coming right at us. So I'll line up that left edge and make sure we're in the path. Then we'll drop the vehicle flush to the ground. I'll show you here really quick. And we're inside, of course.
But yeah, that would be a good idea.
There it goes.
That's supposed to happen.
Yeah. And then the spikes also go into the ground. And then there's the probe, right there. And the parachute will pop up when it's at peak flight, just 50 feet up, and it gets sucked into the tornado.
So if everything's worked perfectly, that probe will have gone out of there and ended up in the tornado, spinning around and getting that critical rotational speed.
Yeah, the tornado will pick it up. There's updrafts in the funnel as well. It'll pick up the parachute. It'll spiral around inside, measuring temperature, moisture, and pressure at a rate of 5 times a second.
And all of that will happen.
It's going to one of these years. Hopefully this year.
Good luck. Good luck with that. You never know.
So, there we have it. The Dominator is going to take the place of our woman with the bucket. And its compressed air-powered roof cannon does the job my catapult and paintball gun couldn't. Now all they need to do is find a real-life tornado and park next to it.
Obviously that could take a very long time, so Reed and his team are on their own from now on. No film crew with them, just them and the Dominator, and a very ambitious mission.
It actually takes 6 weeks, but finally Reed and his crew are hot on the heels of a real-life twister. The trick now is to get as close as they dare, close enough to fire a probe straight into its heart. But finding that heart turns out to be pretty tricky.
Close in on it. That's our GPS position. That's the tornado. About 2 miles to our southeast. We're getting real close. It's right here. Hope we
A tornado can travel at about 70 miles an hour across the ground.
Right here, guys, stop right here.
And change direction frequently and without warning, which makes getting ahead of one incredibly difficult. And they need to get to it quick. The lifespan of the average twister is just 5 to 10 short minutes.
All right, just go, just go.
There it is. On the horizon. See? Tornado on the ground. Right there. Straight ahead. Got it, got it, got it. Straight ahead. Go! Oh, that's huge.
It is huge. About 100 meters across and at least a kilometer tall.
Perfect. Fix it. Look, stop. Stop. Oh my God.
The tornado is coming straight for them.
Coming right at us. Get ready to shoot. Right here.
It's perfect.
Boy, Kevin. Boy! Drop it down!
Not the best time for the Dominator's window to fail.
Roll your window up, Reed. Roll your window up. Good, all right. Boy, tell me when. Right here. We're in it. We're in it. We're in it. Shoot! Shoot the ball! It's right there next to us! I see you go all the way around. It went one full revolution.
It's in. They got the probe inside.
I saw it make one full revolution, then I lost visual on it, so I know it at least went around one time.
But that's only half the challenge. Now they need to retrieve it to find out what it recorded. They wait for the storm to pass, then set off out through the trail of devastation in search of the probe.
So how far ahead do you think it is?
It's probably about 3 miles, I would say.
For some reason, they're not picking up its GPS signal, so they're reduced to searching on foot.
When I launched it, I saw it go out over the road that way, spun around like this, all the way around, and it descended either behind these trees or these trees right here. So we're within a couple 100 feet of it right now. Okay, so it's got to be somewhere over this way, over here. I had full visual.
Against all the odds, they spot it. But the probe is damaged. Its trip around the twister has torn away the housing, leaving the electronics exposed. So were they successful? The moment I get word, I'm straight on to Reed to find out.
Hi, Reed.
Hey, Richard.
You got the thing into a tornado.
Yes, we did.
Was that a special moment?
It was a very special moment,
Yeah.
and it was a very scary moment, too, honestly. I think I might be getting a little too old for these tornado intercepts, but our ears were popping from the pressure fall. It was a pretty intense tornado, and seeing the probe take off was definitely an amazing feeling.
So you've got it. You've got the probe.
Yep.
The information is stored on it, and what we want to know is the speed at the base and at the different heights in the tornado. That data is possibly on the probe.
I'm betting it's on the probe.
Okay.
But we'll be able to get it off here. It should be any week, any day now. And
We've got so close. I mean, yeah, there it is. A lot of
We'll do
that.
both of them.
Okay.
Reed and his team have accomplished something that no one has ever done before. They've managed to get a flying probe into the base of a tornado.
We did it! Today is the first time we've recovered one that we know is inside a tornado. So this is a huge success for our science mission, and I'd say this is definitely a stepping stone for things to come in the future.
It's a proud moment. Unfortunately, the probe turned out to be too badly damaged, so they're planning on doing it all over again. We've discovered what winds are and how they begin, how their paths can be used to predict the weather. We've seen the way a wind can start to spin, and how spinning winds are the basis for much of our extreme weather. More than anything, we're one step closer to revealing one of weather's greatest mysteries: how fast a tornado can spin. But for the moment, the actual answer is still a weather secret. Weather, one of the most astonishing forces on Earth, capable of both devastating power and spectacular beauty. Wherever you live on the planet, weather shapes your world. Yet for most of us, how it works is a mystery. To really understand weather, you have to get inside it. So I'm going to strip weather back to basics.
All in the name of science.
Uncovering its secrets in a series of brave, ambitious, and sometimes just plain unlikely experiments.
Well, it certainly feels like a dust storm from here.
To show you weather like you've never seen it before. Water lies at the heart of our weather, but not just as rain. Because water can transform itself, redefining its powers in the process, creating the fastest, the slowest, the softest, and the hardest weather on Earth. Often changing from one to another with alarming speed and striking consequences. In this program, I'll reveal water in all its shapes. I'll capture a cloud.
Okay, little cloud, let's see what you got.
To see just how much it weighs. Discover why hailstones are able to do so much damage.
Oh, look at that.
Find out what would happen if rain fell in one big lump.
It's amazing, isn't it?
And I'll experience water in its most ferociously powerful form, as an avalanche.
I'm speechless. Genuinely speechless.
All our everyday weather appears to come from the clouds. They're the best clues most of us have as to what the weather is likely to do next. They dictate if it's sunny or dull. And they're where all our watery weather seems to come from. But how? What exactly is a cloud?
Come on, you've done it. If not, you should. Gazing at clouds, dreaming up shapes. And the next time you do,
two things you should know about clouds that might just change the way you think. Number one, clouds are really heavy. Even that fluffy little cumulus could weigh as much as 2 elephants. And secondly, because of that weight, all clouds are falling slowly, steadily down to Earth.
I know, both those things sound pretty unlikely, which is why I'm going to put them to the test. And I'm going to start by trying to discover just how much a small cloud really does weigh.
Now, I know I'm not the only one who, when presented with a sign on a bench saying wet paint, has to touch the bench just to check it really is. So when I heard that a cloud can weigh as much as 2 elephants, but I had to check it out. The only thing is, it turns out that weighing a cloud is a bit more of a faff than checking to see if paint is wet. Obviously, you can't just hang a cloud off a spring balance or pop it on a set of scales, but you could measure the moisture in it and work it out from that. So I thought, what if we could fly a giant ball of cotton wool into the cloud to gather the moisture? As an idea, it needs a bit of finessing, yes, so I've got an engineering mate of mine to iron out some of the wrinkles, and he came up with this.
Okay, so it's not actually cotton wool. It's an industrial version, ceramic wool. And it's not one solid ball either. My friend reckoned that by making the centre hollow, it would double the amount of wool that came into contact with the cloud. He calls it his sky sponge.
And then we've got that to put it in the cloud. It's all fairly standard stuff.
So, first off, let's check how much this sky sponge weighs dry. That's 37 kilos, which for a sponge is already pretty heavy. But we need that weight to be able to fly it accurately, especially when the pilot is someone not that used to carrying freight. I know, it's not a good start. But as nobody has ever done anything like this before, I'm as good a choice as anybody. In the end, it was deemed not a job for an amateur, no matter how enthusiastic. So I took a co-pilot, Andrew, with me to keep an eye on things, mostly on me.
So, helicopter, check. Basket full of highly absorbent ceramic wool, check. All I need now is a nice little cloud to dip it into.
And that's not as easy as you might think. Because when you get close to them, clouds are, well, they're enormous.
You look at them from the ground, they all look perfect and fluffy and small. Get up and they look entirely different. I've got to find a nice individual one, drop it in and see how much water it pulls out of it. I'm assuming it won't soak up the entire cloud and we'll be left with underslung the weight of 2 elephants. That'd be bad.
A full-grown African elephant weighs on average 4.5 tons. A quarter of that would pull my helicopter straight out of the air. But if I just weigh a fraction of a cloud, then multiply my results, it should give us some idea how much a whole cloud actually weighs.
Pick a victim.
What about the one in front up here?
Yeah, that's a nice one. Right, cloud has been sourced. It is quite important that the helicopter itself doesn't go in the cloud. You have to remain visual with, well, pretty much everything.
I need to fly low enough to dip the sky sponge into the cloud, but high enough to keep the chopper above it. Which is trickier than it sounds. Well, for me.
Oh, great. Well, that's all round bad.
First time round, I missed the cloud altogether.
This is a fairly unusual exercise, cloud collecting.
Yeah, that's my excuse anyway.
This one will do a treat. Okay, little cloud, let's see what you got.
Close up, the cloud seems so wispy, it's hard to imagine we're going to soak any water up at all. Okay, we dipped it. Let's get this thing down and see what we've got. Well, it's wet. That's a start. But how wet? Have we managed to collect enough moisture to make a difference on the scales? We have 10 whole kilograms of difference. I know that doesn't sound like much, but look at the size of the cloud. Then look how much of it the sky sponge flew through. Just that small section had 10 kilos of water in it. If every section that size weighs the same, then that little cloud must be getting on for, well, not quite 9 tons, but a lot. And a good-sized thundercloud might be 10 kilometers tall and 10 kilometers wide, which would make its total weight more like 1,000,000 elephants. Or if you prefer, about 60,000 jumbo jets. So how on earth does all that weight stay up there? To find that out, we're going to have to build a cloud of our own. Right, what I've asked to achieve here is an indoor cloud. What I've got is a cattle trough full of water, and I don't even know what these things are. Fortunately, what I've also got is Jim, who is an atmospheric scientist and can hopefully help. What is this? How's it going to work?
So this is how we're going to make something akin to clouds.
Right.
And obviously, it's not a cloud, but it's the closest we've got to a cloud making machine.
Right.
So what we've got in here are some ultrasonic humidifiers. So you quite often see these sort of things at garden centres and things like that. They just produce very, very fine mist.
Garden centres. It's sounding less high-tech now, I'll be honest.
They're masquerading as nice ornamental devices, but secretly they're cloud-making devices.
Well, there we go. Well, come on then, make it work.
So all I need to do is turn this on.
Oh, hello.
There you go.
Suddenly, miniature clouds appear.
And that's just by breaking the water molecules down into smaller bits?
We're breaking the liquid water
Yeah.
into just very, very tiny droplets of water.
These garden pond devices turn the water into tiny droplets. And that is exactly how a cloud works. Clouds float because the water drops inside them are so small and so light.
What's the difference in size? How big is a droplet of this compared with a droplet?
So a droplet of that is 5 microns, but that means absolutely nothing to you.
Small.
Okay. So, but a rain droplet, you can get your head around the size of a rain droplet. A rain droplet is about 2 millimeters. So the difference in size between these and the rain droplet is the same as if you've got a sugar cube and a caravan.
Hang on, which is the caravan?
So the caravan is the rain droplet.
Right.
And the sugar cube is these tiny little droplets.
Right, well that is working.
The humidifiers have split all our caravans up into billions of sugar cubes.
Okay, lid goes on.
Okay.
But to really complete the effect, we want to see if we can get those tiny moisture droplets to float in the air.
We'll turn the fan on now and we'll see our clouds emerge.
There it is.
Weirdly, it feels dry. Hard to believe our sky sponge managed to soak this stuff up.
So this isn't just something that looks a bit like a cloud, this is pretty close to a cloud.
But these are just droplets of water, very, very small droplets of water, and that's what a cloud is.
That's a cloud. Jim, not being critical of your cloud, but it looks a lot more frantic. I think of clouds as just solid state, really, just drifting.
What you're seeing here is what's happening around the edge of a cloud. It's constantly changing.
So you get up close to a cloud and it's really quite busy.
Yes.
So whilst I'm very impressed with your homemade cloud here, it's kind of not up enough.
Now, this might look like overkill, but actually our cattle trough is surprisingly heavy. Just like the water in a real cloud. And I do need to get all that water off the ground to check that second fact. Are all clouds really falling back to Earth? Jim and I wait with bated breath. We might have made the water droplets small enough to float, but it's true. Once they're up in the air, they drift back towards the ground.
So this effect where I can see it rolling over the top and then sort of falling, that's accurate?
Yes. Our cloud is dropping out. So if you look at clouds with binoculars or something like that, you'll see bits of streams of cloud.
So because this is small, it all looks faster, but if this were as big as a real cloud, this effect, this exact effect, is what's going on all the time?
Yes, just continuously, all the time, around the edges of clouds, around the periphery of clouds, we've got this process going on all the time.
So there you have it. Clouds are heavy, and they are all falling slowly down to Earth. It's just that most evaporate before they ever get there. In fact, the typical lifespan of a small cumulus cloud is only 10 to 15 minutes. But while they're up there, they act as a sort of public transport system for water, carrying it from one place to another. Until either the service goes off duty, or they dump all their passengers out as rain. There are about 13 trillion tons of water being moved around in the atmosphere. And every day, about 1/10 of that comes crashing back down to Earth. Sometimes these storms are incredibly intense. The quickest on record dumped 12 centimeters of water in just 8 minutes. The heaviest managed nearly 1.5 meters of rain in under 10 hours. And so to my home territory, where on average it rains 1 day out of every 3.
This is my favourite place in the entire world. It's in the Lake District, Honister Pass, running down to Lake Buttermere. I've been coming here for 27 years. It has one of the best views in the world. I've seen it once,
That's because this specific place is the wettest in England. On average, 4 meters of rain falls here every year. And yet, on the one day when I am here specifically to talk to you about rain, it's not actually raining. We've had to resort to this.
Yes, sprinklers in the wettest place in England.
However, this will suffice perfectly to allow me to show you what I want to show you.
Puddles. Puddles hold the key to seeing how those tiny cloud droplets turn into raindrops. We can't look into a cloud to see how raindrops form, but we can get an idea of what's going on by looking in a puddle. As the raindrop hits, part of it is attracted to the water. What bounces back up is a smaller droplet, about half the size. When that droplet hits, the same thing happens again. Around half of it stays in the puddle. Now imagine that in reverse and upside down. The puddle is the cloud. A water droplet doubles in size by attracting other water droplets. These stick on in a process scientists call coalescence. It increases again and again until it's so heavy it falls away. And that is, roughly, how rain is formed.
It feels right like this. This is how it feels here.
Which is just as well, because I've got one more thing I want to tell you before I get them to turn these sprinklers off. And it's about the official difference between rain and drizzle. Look closely at a puddle's surface. If the drops are splashing, like here, then it is rain. But if there are no splashes, then it only qualifies as drizzle. Officially. Clever, isn't it? Splashes, rain. No splashes, drizzle. But what they've both got in common is that they're just too heavy to be held aloft.
We talk about heavy rain, but water is heavy, very heavy. To give us an idea of just how heavy, we are about to see what would happen if all of Borrowdale's 4 meters of water fell in one go.
Now, obviously, we can't get a digger the size of the Lake District. So we're just going to recreate what it's like when 4 meters of water hits one small area.
So we have 4 cubic meters of water in the bucket, which amounts to 4 tons at height. Then beneath it, you'll see we've found a car for scientific purposes.
Let's see just how much damage that amount of water can do. Looks like rain. Yeah, pretty brutal. But I shouldn't be surprised, because the water actually weighed 4 times more than the car underneath it. Every minute of every day, 900 million tons of rain land on our planet. That's about the same amount of water as in all 16 lakes of the Lake District.
Oh, they're going to notice. But it does prove the point. Water is really heavy. That is just the annual rainfall for Borrowdale, where I've been going on holiday all of my life. Explains something about it. It's amazing, isn't it?
Luckily, this could never happen with real rain. Not even in a tropical storm, where sometimes it feels that the heavens have literally opened. Partly because, as we saw earlier, raindrops fall the moment they get heavy enough. And partly because of what happens to rain as it falls. To show you what I mean, I'm hard at work building a sandcastle. And Professor Jane Rickson from Cranfield University is filling a plastic bucket from a pond.
There were always kids like you on the beach, weren't there?
Okay, so what's all this about? Well, pour water on a sandcastle and you completely flatten it. No surprises there. But rain doesn't fall from waist height. It falls from clouds that are at least 300 meters above the ground. And that makes all the difference. Let me show you by building another sandcastle and throwing the water off something just a little bit higher.
Now, obviously, this isn't as high as a real cloud. They start at around 300 meters. This tower is 30, but it's tall enough for what we want to do.
Okay, Richard, let it go. Idiot.
Yeah, wrong side. How was I to know? Let's try it again.
Okay, Richard, let it fall.
And so, another bucketful leaves the tower, but what arrives below is rain.
And there it is, still standing. So, why? Why is it if I throw the water from up there, you'd think it would smash it to bits even more, but it's still standing. What's the difference?
Well, what happens is you were throwing that water down, air resistance, the turbulence in the air is overcoming the surface tension of that lump of water, breaking it into smaller drops. Do you want to go and see that? Should we do it again?
Yes, I'll get the water.
As the water falls, it meets air resistance. And the larger the lump of water, the more resistance it experiences. That friction breaks the water up into smaller pieces, sometimes inflating the drops like parachutes before blowing them apart. The further they fall, the smaller those drops become, until finally they're so small that the air has little effect on them, and they land as rain.
So that's why the water landed in drops and didn't smash it, rather than a big bucket-shaped lump.
That's right. And in fact, you can actually see the point at which that lump starts to break up into those smaller drops.
Well, you can if I climb the tower again. It actually happens surprisingly quickly. Within 10 meters, there's enough air blowing on our bucketful of water to break it down into drops. If our digger had been just a few meters higher, then the car might well have survived. So even if it was possible for water to fall out of the sky in one big lump, by the time it got to the ground, it would still be rain. Because they break down like this, the average raindrop ends up about 2 millimeters across. But there is a way that water can fall out of the air in bigger, more dangerous pieces. By shape-shifting into ice. Now, most of us think that when we see ice falling out of the sky, it's hail.
So what if I told you this wasn't hail at all? Sure, it looks like hail, but it can't be hail. You can't get hail in winter. It only happens in summer. I know, you think you've seen hail in winter, but trust me, you haven't. What you've seen is this, ice pellet. Ice pellets are formed when a snowflake partially melts on the way down, losing all its pretty branches, and then refreezes, forming a small ball before it hits the ground. Just to make things even more confusing, in North America they call this sleet, which over here means a sort of slushy mix of rain and snow. Either way, this is not hail. Hail is something entirely different.
Charles Knight has been studying hailstones for the last 50 years. And in his refrigerated laboratory in Boulder, Colorado, he offers to show me exactly how hailstones are different by sawing one in half.
It's very simple. We just use a hobby bandsaw like this.
You're just going to slice it in half?
Yes.
How long have you had that hailstone?
Oh, about 10 years, actually.
What? But it's worth it. As soon as Charles opens it up, the difference is revealed. Hail is made of layers.
And there you can see one layer there anyway.
So where there's that little circle?
Yes. But in the bigger hailstones, there's much more obvious layering. This is an example of really what you would call a giant hailstone.
It's enormous.
It's enormous,
Yeah.
Yes.
But that's obviously not going to stop him cutting it in half, even though this one is 15 years old. Oh, wow! This time, the layers are crystal clear.
If you make a thin section, then you can really see the layering.
That's a slice right through it. That's absolutely beautiful. That's really telling its own story, isn't it? Just like the rings of a tree, these layers chart the story of how this hailstone grew. It's a story that starts with a thunderstorm. And thunderstorms only tend to happen in summer. Because of the height of thunderclouds, some of the water droplets inside them freeze. But the powerful updrafts created by the warm weather keep the droplets supported in the cloud, where they collect more water, with new layers freezing on in a separate shell. Until finally, there are so many layers that they're too heavy to be supported and they fall to the ground.
Which got me thinking, because it's made in layers, does that mean hail is stronger than a single solid ball of ice? You make wood stronger by laminating it. You make glass stronger by laminating it. So does laminating ice make it stronger?
Certainly hail is powerful. It causes over £1 billion worth of damage a year. But is it any harder than conventional ice?
To find out, we're going to have to go into uncharted territory with an experiment that hasn't been done before, using that. Yeah, I know, it looks like a length of plastic pipe on some tables in a field, and to some extent, well, it is. But you should see what it's about to do to that table tennis bat.
Its inventors, Purdue University's Jim Stratton and Craig Zaring, wanted to see just how fast they could get an ordinary ping pong ball to fly. And the answer, using this contraption, turns out to be very fast indeed.
That is astonishing. This projectile is moving when it comes out of there.
Oh, yeah. About 919 miles an hour.
Yeah, that's brisk, isn't it? Yeah. So you brought along your device, which is, if you think about it, a sort of nightmarish automatic serving machine, and you've agreed to help us.
Mm-hmm. Yeah.
OK, right. So here's the plan. We're going to see which is harder, ice or hail. But first of all, we've got to make some hailstones.
We've already seen how much of a faff that is, even for Mother Nature. But luckily, Jim and Craig have a plan. A plan that starts with dry ice.
It's like an 80s pop video.
A pop video starring a bead on a bit of string. The dry ice makes the bead really, really cold.
2 rolls.
Yep.
Before it's dropped into cold water.
If you'll notice, every time he puts it in there, you can hear just a little bit of a crack. You can hear a little bit of fizz, and that's the water instantaneously freezing to the outside.
So that's 1 layer of ice around that little
Very
seeding
small layer,
leaf.
yep, very small layer.
How long does this take?
About 10 minutes.
Oh, God.
How many of these do we need?
Quite a few.
Oh.
And they need to be the size of ping pong balls to fire them from Jim and Craig's gun.
Can I have a go?
Yeah.
Right, dip it in here. Fairly quickly into there. That's it.
Yep.
Look at that. It's already the size of a pea. I'm just suggesting we probably need to find a way of mass producing these. I mean, this is the land of Henry Ford.
Right.
One is good. We can try 3.
And now you've tripled your efficiency.
Haven't I? Haven't I? Sometimes on TV we don't do things in actual time.
Mm-hmm.
This is one of those occasions.
You gonna do anything?
Reading this.
There's no words, you're just looking at the pictures.
My turn again.
Yes.
Oh, you've been busy.
Hail's ready.
They're done.
They are done.
Magnificent they are as well. Look at that.
OK, they might need a little bit of rounding off to get them down the barrel of the gun, but the size is good.
Say goodbye.
1.
Excellent.
2.
3 of 30.
We're going to have to do some more, aren't we?
Really?
Yeah. A whole bunch. Yeah, OK.
So we have something to compare them with. We've also frozen some water into ordinary ice, using a few of Craig and Jim's spare ping pong balls as molds. So we've got solid ice and we've got hail, which is ice in layers. Time to put them up against each other to see if there really is a difference. And we can't resist starting with one of our homemade hailstones.
I'll give you the honors. All you have to do is punch it.
Let me scoot back a little bit so we can look
Why
at
is everybody else standing back?
Well, I'm getting so we can see.
Right. What? I've not done this before, have I? How wrong can it go? Are we ready?
Yep, we're ready.
Punching a hole in there now. It's quite dramatic, as it turns out. Yeah, let's have a look at the footage.
Believe it or not, we're breaking new scientific ground here. So to make sure we capture any differences between the ice and the hail, we're recording everything at ultra-high speed. And sure enough, our cameras capture every detail, from the plastic seal popping off the tube to our hurtling hailstone punching through the target.
Oh, look at that!
That is awesome.
Beautiful.
Is it worth experimenting now with just seeing how much more resilient one is than the other?
Yeah, we brought plenty of materials we can shoot at, so we can actually shoot two of them at the same thing and see what one will go through, one won't go through, and the type of force that we have in there.
That's exactly what I was meaning. Do that. Right, let's do it.
So here's the setup. We've got lots of different sorts of wood, and we're going to take 2 shots at each piece. First with plain ice, then with our homemade hail. First up, chipboard.
Right.
3, 2, 1.
Ice, straight through. Hail, straight through. Okay, slightly thicker piece of chipboard. Same result. Plywood. The ice barely dents it. Come on, hail.
3, 2, 1.
Well, there is a difference. The hail splintered the back of the plywood. Let's try a slightly thinner piece. This time, the ice barely makes it through. The hole it makes is far smaller than the projectile itself. Right, fingers crossed.
Woo, nice.
That's awesome.
Did it work? What happened
It
at the
did.
other end?
It smashed, and there's your impact.
Yeah, and that's right the way through.
Yeah.
Yep.
In fact, that's completely different.
Same piece of wood, same shooting speed, different results. In slow-mo, you can clearly see how much of the ice ball never makes it through the board.
Well, it might be crude, but that is what I hoped we'd see. This mark here, that's from the straight ice, barely getting through. That is our homemade hail with its laminated layers around it. Clearly, a more fearsome projectile.
Both balls are made of frozen water, so you wouldn't expect any difference in how hard they are. But the layers in hail do appear to make it stronger. So summer hail does seem to be harder than winter ice. But water can shapeshift into something even more dangerous. Naturally quicker than hail, with a mightier punch than hail. And what it is might well surprise you. This is how most of us are used to seeing snow move. Delicate flakes floating gently down to earth. Floating so gently that a snowflake can take nearly an hour before it finally reaches the ground. Traveling at just 4 miles an hour, little more than walking speed. And yet snow can be the fastest form of water that there is. Because when it's in an avalanche, it can hit 80 miles an hour in 6 seconds flat. And then, well, it just keeps on accelerating. The fastest one ever recorded on Mount St. Helens in America clocked a staggering 250 miles an hour. So how can snow move down a mountain faster than water can? Walter Steinkogler of the Institute for Snow and Avalanche Research is trying to find out how that incredible speed is possible by starting an avalanche of his own.
Walter. Yes. Is this where it's going to happen? That's
Absolutely, absolutely. You can see it quite nicely now. This is the
Yeah.
whole slope. You see 2 spontaneous avalanches already, and we're gonna try to release the avalanches from the very top.
Well, don't those 2 avalanches mean it's already happened? It's all over.
No, not at all. You see there's plenty of snow still on the slope.
Okay.
And actually this is a really good indicator for us that there is the potential to produce nice avalanches.
And then when that's going on, you're going to be conducting experiments and
Yes.
learning. I mean, this is part of an ongoing piece of work for you, isn't it?
It is. It is actually part of my PhD thesis, and this data is really essential for my work, yes.
Right.
There are several different types of avalanche, but the fastest by far is what's known as a dry powder avalanche. And that's the type we're hoping to get. If he can trigger a dry powder avalanche, Walter can find out more about how they move so fast. And we've offered to help by putting a barrage of slow-motion cameras on the slope.
We're not going to mess up your PhD.
I will tell you afterwards, but I would appreciate if you don't do that.
I will. If I do, send him the bill.
Oh,
He's the
I
director,
sent to this
That's
guy?
Graham there.
Perfect,
Yeah,
yes, I will do.
He's in charge. I'm not.
Let's hope it doesn't come to that. But I would like to add an extra element into his experiment.
So, Walter, can I place these on the slope? If they're a known distance apart, I thought I could time when the head,
We call it the front.
the front of the avalanche passes one of these.
Yes.
I can time it over that distance and I can work out how fast it's going.
Sure. That's a nice approach. You can do that, yeah?
Thank you very much. Right, we'll do it. I just need a helicopter.
Okay, well that's that sorted. But now we need to work out how to fly our fences into precise positions without triggering an avalanche ourselves. Our safety team have been thinking long and hard about the best way to do it. And what they've come up with is dangling someone on a bit of rope. This someone, in fact, who apparently enjoys this kind of thing.
That is the single coolest thing I have ever witnessed. That man is without a doubt the best helicopter pilot I've ever seen in action.
I mean, that sky sponge was difficult enough.
Just to be flying that close to mountains and sheer rock faces in this gusty, windy, changeable weather. Just that, let alone with another bloke dangling from a piece of rope below you, and then below that a huge, well, basically wooden sail. I'm speechless, genuinely speechless.
Walter has told us where he expects the avalanche to fall, so we position the first fence slap bang in its path. But the conditions up here are very changeable, as we discover when we try to fly the second fence in. Suddenly, the winds quicken and start to gust alarmingly. At any moment, the whole fence could be dashed into the side of the mountain, taking that bloke with it. Not to mention the helicopter. And the fence needs to be exactly 100 meters from the first one. Never have the words "rather him than me" been more directly applicable. It's down.
So everything is now in place. My two boards I know are 100 metres apart. When the front of the avalanche passes the first one, I'll start the stopwatch on my phone, stop it when it passes the second, and we'll get an idea of the speed. And I do know we're going to be surprised. How something that a little snowflake can take an hour to drift down out of the sky can suddenly be part of something so fast and so powerful.
All we have to do now is wait for them to trigger it.
That obviously is the explosive.
Okay, we're off. Fence one, fence two.
Oh. Well, my boards have gone.
I missed it. But I suppose it does prove, in a way, just how fast an avalanche can be. And luckily for me, our slow motion cameras captured everything. So let's take a look at that avalanche again. This is the moment the dynamite is dropped from the helicopter, causing this explosion at the top of the mountain. Immediately it's surrounded by a powder cloud, made up of 1% snow and 99% air. This is a dry powder avalanche. The avalanche accelerates down the steep incline until it reaches our first fence, though not exactly at the angle we expected. The leading edge passes the first one now, and that particular bit of snow reaches the second fence now. Almost exactly the same time the first fence is destroyed. No wonder I had trouble timing it. Our avalanche was actually only travelling at 25 miles an hour, just a tenth of the speed of the fastest one ever measured, but still faster than if we'd just pushed that snow over a cliff. I want to know how that's possible.
Let's imagine there's a chunk of snow at the top, and then it starts to move. What's happening to that snow from the moment it starts to move down?
Well, first it will break into pieces and it gets rounded a bit, and it also gets compressed.
And these are the pieces which you can see up there. They look like snowballs.
Technically, most of them are snowballs, yes.
These snowballs are the secret of what's going on underneath that powder cloud. Walter offers to show me how.
Okay, Walter, this is like an avalanche. How?
Well, you imagine an avalanche that's moving down a slope. It's gonna pick up snow like you are doing now, and it's gonna put it in motion, as in our tumbler here. It seems you're losing your motivation. Come on, keep on going. One more. You can do it. You can do it. Come on, Richard. Perfect. I think we're good there. And you can see already it's compacting, then it's breaking apart again, then it's compacting again, and at some point you will end up with ball-shaped features.
It is magically making
snowballs.
A mixer full of snowballs, yeah.
It makes snowballs. Of course, in an avalanche, this is happening much faster, and it's much more violent process going on there.
But this is a slowed down version of exactly the same process, and you can see that sort of grinding, rolling motion you can imagine happening.
Perfect. Yeah, that's exactly the case. Yeah, true.
So understanding this will allow you to understand more about how fast it might go, where it might go, how it will behave.
Absolutely. I would say they are quite done. Yeah,
Can I
yeah.
turn it off?
Perfect. Yeah, turn it off, please. Yeah.
So in here, snowballs.
Perfect snowballs, right? Aren't they?
I mean, that's seriously packed.
It's quite hard, right? I mean, it would be not that nice to throw it on a person, I guess, this one.
Are you looking over there and thinking targets? Because I was. That's
Oh,
wrong.
they're cross-country runners? Come on, do it. Come on, do it. He was scared for a second. Did you see?
Walter wants to excavate the avalanche to see how much snow it contained. And I follow him into, well, a big hole. Because I want to be sure whether it's these snowballs that make the avalanche move so fast.
This is not that easy to answer because still going on ongoing research, but for sure it defines the motion of the avalanche, yes.
So you can't say for definite yet as scientists, and I love it when you guys can't give a definitive answer.
Yes,
It's
I
great.
cannot
You're in a
because
corner.
it's my research, and if
Yeah.
I say it now, I mean I need to publish this stuff first.
So would you ever end up with your avalanche effectively rolling along on like ball bearings? Or like when they used to build huge, you know, they'd get a huge stone and move it to one place to put it up as a monument, they'd roll it along on logs, wouldn't they? Is it like that?
I think you can kind of say it like that, yeah? I'm from a scientific point of view, I'm not 100% sure.
You
I have
think
to
that's
admit.
rubbish, don't you?
No, no, no.
Be
I'm not saying-
honest.
no,
Come
no,
on,
no,
you
I'm not
big
saying-
old
no,
dude. You
no,
go,
no,
no,
no.
from a scientific point of view, I'm not sure. It just says rubbish.
Now, there are studies that say that really it's the ratio between the bigger grains or the bigger balls to the smaller balls that can significantly influence the speed and the motion of the avalanche. So you're not that far off, actually, with your comparison.
Maybe you're just jealous because it was my idea.
Yes, I know. But yeah, no.
That's what it is.
You can publish that, actually. That would be something for
But I have to write it up.
Yeah, but you can go into research.
I can't be bothered, take ages.
No,
You can
no,
have it.
no,
Have
no,
it.
no.
It's yours.
Okay, then I
It's
do
yours.
it.
Yeah, have it. It's yours.
Put something on wheels and it can accelerate quicker than if you simply drop it. And these snowballs may be the wheels of a dry powder avalanche. Snow is the softest, lightest way that water can fall to Earth. But an avalanche can move faster than any other type of water. 4 times faster than the fastest flash flood ever measured. And it seems snowballs might well be the secret. Of all the water on our blue planet, only a tiny fraction is actually in the atmosphere. Yet water's incredible powers of transformation mean that that's enough to bring us all our clouds, rain, hail, and snow. And with it, all the everyday weather on Earth. Weather, one of the most astonishing forces on Earth. Capable of both devastating power and spectacular beauty. Wherever you live on the planet, weather shapes your world. Yet for most of us, how it works is a mystery. To really understand weather, you have to get inside it. So I'm going to strip weather back to basics.
All in the name of science.
Uncovering its secrets in a series of brave, ambitious, and sometimes just plain unlikely experiments.
Well, it certainly feels like a dust storm from here.
To show you weather like you've never seen it before. All weather, no matter how rare or how unusual, can be broken down into 3 simple ingredients: wind, water, and temperature. With just those 3 things, you can create pretty much any weather you want. But the most important of the 3 is temperature. In this program, I'll discover how without it, we wouldn't have any weather at all.
Oh, yeah. Oh, that's a lot of dust now.
How a dust storm in Africa can make rain right here. And how heat can produce snow as hard as concrete. Almost all our planet's heat is provided by the sun. And we tend to think of the sun as the source of all our best weather.
But if you're looking to unlock the secrets of the weather, the heat coming from up there is not as important as when it's coming from down there, from the ground.
I know it sounds unlikely, but it's all to do with the fact that the sun heats the earth unevenly. Sand gets hotter than water. Tarmac gets hotter than sand. Concrete gets hotter than grass. And these differences produce pockets of warm rising air called thermals, which drive winds and create clouds. But how can you see that effect for yourself? Well, with a quarry, 5 vehicles worth of kit, and 2 specially built metal tables. These tables are going to be our hot ground. Because they're dark in colour, they should soak up lots of heat from the hot sun. And to make sure they get hot enough, we're going to give the sun a little help. With 14 gas canisters, all connected up to 18 high-power burners. We reckon with these we can get our table up to 200 degrees C, maybe even higher. And I'm hoping that's enough to show you what it does to our weather.
To be perfectly clear, my ambition here is not to actually make weather with this. I'm not hoping for a little square cloud overhead. The theory is right, it's just the scale is a bit small. What I will be doing is creating that rising column of air, that thermal, which is part of the weather, and it is something I will be able to show you once I've got it established.
So let's do just that. Turn on the gas, fire up the burners, and get those metal tables as hot as we feasibly can, enabling me to fly some paper helicopters. Yeah, I know, but bear with me.
Hello.
There is method in this.
Can I have my box of... Thank you. Right, going up.
Time for my high-tech thermal indicators. Now, normally, a paper helicopter would just spin slowly to the floor. But it doesn't. It hovers.
Fly! Oh, there you go, there you go, there you go. You can see how we've created a thermal down there, and the helicopters that catch it are flying in that column of rising air.
The updraft is enough to hold the helicopters in place, just as they do naturally with clouds, raindrops, and hailstones.
Oh, yeah!
But as the heat coming off the metal table increases, the helicopters begin to climb, until they're disappearing out of sight, which is how it should be. A real thermal can reach 1,500 meters, and they have an important role to play in our weather. We've all seen how puddles dry up on a hot day, but where does that water go? Well, those thermals take it up into the air until it gets high enough and cold enough that it condenses back into drops and forms a cloud. But there's another result of this uneven heating of the Earth. It produces deserts. And deserts play a very important role in what happens next to those clouds.
It's hard to imagine, I know, but right now I am surrounded by desert. And not just any desert either, probably the most famous desert of them all, the Sahara. And there it is. That is Saharan sand.
And it's not just on this car. It's on all these cars. And this bench. Pretty much everywhere, in fact. Somehow, it's managed to travel a huge distance.
All the way from Africa, more than 2,000 miles away.
So how on earth did it get here? Well, first you need a particularly sun-parched part of the planet. And then you need a dust storm. Dust storms are the way nature gets dust off the ground and into the air. A big one can easily be a mile high and 100 miles wide. A vast, moving wall of dirt. But even the big ones only travel between 25 and 50 miles before they die out. So how does the dust end up 2,000 miles away on the bonnet of a car in Bristol? Well, believe it or not, it bounces there.
Let me try and show you what's going on. Imagine this tennis ball were a grain of sand. Drop it from waist height and it bounces up about 2 feet. Now imagine this ping pong ball were a smaller particle of dust. Drop it from the same height and it bounces up about the same distance. But if I drop them both together, watch what happens then. Yeah, the ping pong ball flies off. What's happening actually is the ping pong ball is smaller and lighter. All the kinetic energy, the bounce in this ball has been transferred into it and away it goes. Obviously, real dust comes in many more than just 2 different sizes, which is why this is maybe a better analogy. 4 different sizes of ball this time, stacked loosely on this plastic spike in the centre. Obviously, real dust doesn't have a plastic spike connecting it, but your alternative is you watch for 10 hours whilst I try and drop all 4 in a line. Let's see what happens this time. It's gone. The small ball is, I mean, it's just, I'd show you again, but I'll have to wait for it to re-enter the atmosphere, I think. Seriously, it's gone.
So that's the principle. But can actual dust really do the same thing? Even with the power of a huge dust storm behind it? To find out, I'm going to the source of most of the world's dust. Not the Sahara, but South Australia, where Dr. Craig Strong has offered to help me start a dust storm of my own.
What are you actually looking for?
Well, I'm looking, Richard, for the landscape that's going to produce dust. And I think this stony plain is probably really good because you can see these rocks. They're acting as a trap for dust. So I think if we dig down, we'll find that there's plenty of dust. It's just that means it hasn't blown away yet because of the rocks are locking all that dust in.
So when I see an area of rocks like this out here, I assume all the dust has gone. You think it's trapped underneath?
Absolutely. So if we have a look down here, Richard, once we get under there, it's just dust gold. You know, look at this.
It's incredibly fine.
And see that just blown away. So there's lots and lots of fine material. This is exactly what we want. That's what dust storms are really made of.
The problem here is that the dust is trapped under these stones. That's why you know it's here, but it is trapped.
Absolutely.
How do we get it out?
The rocks are doing the job of protecting the soil, so I reckon we probably should pick up the rocks and move them out of the way. That's the first step.
Churn it up a bit.
Churn it up a bit, that's right.
That's easy. I can do that for you. I'm going to do it then.
Well, I say me, but actually I mean this chap, Trevor, who just happens to have the very tool for pushing aside all those stones. It's not long before he's cleared an oblong area the size of a couple of football pitches. And it has an immediate effect.
Look at that, dust devil. That's amazing. Probably those swirling winds come through here all the time, but because we've taken the stones away and uncovered the dust for it to be picked up, we can suddenly see them. It's beautiful.
But it's not what we're looking for. We want to make something just that little bit bigger.
One dust storm coming right up. Right, where do you want it? Here, I would say. This'll do nicely. Doing this in what is effectively the home of half of the world's dust. Hope I don't trigger an international incident. You get up tomorrow and your sideboard's covered in dust, because I started this. That's a lot of dust. I don't know who that bloke is. Just a helpful local decided to lend a hand. That's good of him. Kind of blokes live around here, happy to come out, all in the name of science. Yeah! Now we're talking. This is a dust storm. Oh, that's a lot of dust now.
And it seems to be working. In amongst all the cars and chaos, the dust is starting to bounce. Individual grains are colliding against each other, just like the rubber balls did. And notice that they're not just bouncing in the direction of the wind, they're being propelled upwards.
Well, there it is. We've got the dust bouncing just like it does in a real dust storm. But in a real dust storm, it bounces much higher than the storm itself. Can we do that here today? There is only one way to find out.
Craig has brought in another dust expert to help, Professor Nigel Tapper, who specialises in measuring airborne dust. With his assistance, we should be able to see just how high we can get our dust to bounce.
Okay, beautiful. Nigel, to be honest, it looks like this is something you're about to fire at your balloon. What is it?
We've got a pump arrangement here that pumps at about 2.5 litres per minute through this cyclone sampler that we can put underneath the balloon to sample dust at various levels. That was a fly.
Yeah, they're quite tasty.
And, yeah, they're
good.
beautiful.
They're not bad. They're not
They're
bad.
particularly tasty here at
Bit
Balloon.
dry.
Yeah.
So tie it onto the balloon string then.
Yep. I just got to run it through here. This is the tricky bit because you've got to remember which way to roll it.
Oh yeah.
There
I'll
we
do
go.
this one. I'll do
and
this
we do it on the bottom too.
Watch this go well.
Yeah,
Hold
you
on.
do
It's
that.
that. I've got it. No, watch. It's that way.
Ah, perfect.
You
Yeah,
see?
well. You've done that before.
Well, no. Why would I have done this before? Ever?
Okay. Winching up.
We're winching, not whinging. That's a pom joke.
Yeah, I know.
Yeah, all right. I just chucked it in.
Nigel plans to put 3 dust samplers under the balloon. One at 3 metres, which was about the height of the cloud we created with the cars. One at 8 metres, more than double that height. And one at 20 metres, because, well, that's how much string we've got. That extra vane at the top is carrying a miniature camera, so we can keep a close eye on what's going on. And to make sure we're doing our very best impression of a real dust storm, we've wheeled in a couple of enormous fans to supply some extra wind.
So my job now is to try and keep the balloon, which is suspended from the winch over there through this hook, at the right height and in the best place to catch the most dust kicked up by our dust storm. And one important thing to bear in mind, this all seems very big. I mean, it's a very big balloon, we're using big tools to make the dust, but we're imitating the weather. This whole experiment, in fact, is tiny, but the principles are just the same. And hopefully the fine particles will end up on top. Or me, if this balloon goes much higher. I did point out to them I'm the smallest bloke here. Why I've got this job, I don't know. We'll be all right. Right, we're ready. So the vehicle is churning the surface. The fans do the job of the wind. Maybe I should have put my goggles on. That would have been better. Well, it certainly feels like a dust storm from here.
So now I just need to keep the balloon in the densest part of it.
I'm going to go over here a little bit.
Basically, if I can't see or breathe, then I'm probably in the right spot.
The different pumps at different levels are sampling the air and the dust carried by it at different heights. There's no way could these fans actually blow the dust directly onto 10 or 12 metres, but they do inject the energy into the system. It's an exchange kinetically, the particles bouncing off one another, hopefully ending up at the top.
But there's only one way to know for sure. Check what's in those pumps. Luckily, Nigel has a makeshift laboratory right on site.
It'll be really interesting to crack these open and see what we've got. We've got to be a little bit clean here.
What are you trying to say?
All right, now we've got the insults out of the way, time to see what we collected in the lowest pump. And if it's not dust, we've got a problem. Because that was slap bang in the middle of our homemade dust storm.
Okay, beautiful.
Oh, there it is.
We were only sampling for a short time, and there's a lot of it, as
Yeah.
you can see.
So let's move up a level
Okay.
to 8 metres up into our homemade dust storm and see what
That's right. So let's have a look at the filter paper. Turn it over. Whoops, we've got a slide there with
Oh, there
a
it is.
little bit of smudging.
Yeah.
So we've actually got a bit of fine material at 8 metres.
So now at 20 metres.
At 20 metres.
Which was well out of the actual
Absolutely.
cloud of dust. If there is any here, this is the finer particles that have managed to bounce themselves up well beyond the top of our plume of dust.
Come on. Turn it up the right way. There we go. Well, look.
There is smudging on.
There is a smudge, so we did get a bit of material up that far.
Definitely some there.
So I think we can count that as a success. We've got dust at least 5 times higher than our cloud.
So we must bear in mind, this experiment, though to us it was quite big, it's actually tiny. In terms of the weather, it was minute. So this upper level, for us 20 metres, that was outside of our plume of dust.
Right. Yeah.
If that were scaled up to be weather, to be a dust storm, that could be thousands of feet high.
If we were looking at a real dust storm, and they could get up to 2,000 to 3,000 metres, it's an amazing process.
A large dust storm can move 15 million tons of sand in a single go. Many are so big that they can be seen from space. And when that dust has bounced high enough, it gets caught in global wind patterns, which move it around the planet. Once in the clouds, dust plays a crucial role in our weather. Because dust is central to the story of rain. Water vapor needs something to stick to if it's going to turn into raindrops. And dust is perfect. So down the dust comes, carried by the water drops. Out of the sky and onto your car. So without the sun beating down, creating deserts and dust, you might not get rain. Kind of ironic, isn't it? But there is one rare type of rain that doesn't need dust. What it does need is cold.
It's a weather phenomenon unlike any other. One that can take any of these objects and trap them like flies in amber, encasing them in a hard, plastic-looking shell.
It's called freezing rain. And as its name suggests, it's completely dependent on temperature. But it's not just the weather that needs to be below freezing. The rainwater does.
And I'm going to try and recreate it for you, right here, right now. Actually, I'm probably in the best possible place to do that, Montreal, Quebec, Canada, because it happens more here than just about anywhere else in the world. Right. Oh yeah, that's perfect. Really very cold, which is what I want. The air temperature here right now is about -10 degrees C, but as long as it's somewhere near freezing, the air temperature doesn't matter. It's the temperature of these objects.
I need them to be really cold, and they definitely are.
So, I've got water that's below freezing, but it's still in liquid form, and I've got a hose. Let's see what happens when super cold water hits super cold objects. It's not complicated. I've begun.
Well, it might not be complicated, but it is effective. The moment the spray hits the hydrant, it turns instantly to ice. Fully formed blobs of ice that appear right in front of your eyes. Instead of dripping into icicles, it solidifies immediately. So, how does it work? We've already seen how raindrops need an impurity like dust to form. But freezing rain is formed when a snowflake falls through a freak layer of warm air on its way down. Now it's rain, but rain without any dust inside it. The temperature of the drop can go below freezing without turning to ice, until it touches something cold. To try and recreate that, I'm spraying distilled water.
Starting. This, I feel, is good, but it's going to take a while. I could be patient and wait, or just tweak my approach a bit. Bigger, which is better.
The water in the truck has been outside for days, so normally it would be frozen too. But fire trucks in Canada have a constantly revolving drum inside them that keeps the water moving, a bit like a giant slushy drink dispenser.
This is strangely addictive. I mean, I've done a little bit there, and now I just want to do everything, more. Let's have a go at this.
Certainly, it gets the job done quick. So, let's see what we've got.
Look at that. Completely encased in crystal clear ice, and that's exactly what I want.
It's the clarity of the ice that makes freezing rain so unusual. That and the fact that it completely surrounds any object it touches. It's not just icy where the objects face the hose. It's icy everywhere, in a perfect, even coating, leaving the objects rigid but unharmed. Ish.
There's going to be shouting about that.
Luckily, freezing rain is fairly rare, but it does hold the secret of how we get frost. Just like our fire hydrant and phone box, these leaves have cooled below freezing. The difference is, frost grows without falling as a liquid first. The ice crystals just magically appear, literally out of thin air. But when ice crystals grow in the air instead, then something even more magical happens. They become snow.
All snowflakes start off as an ice crystal, a six-sided shape, a bit like this.
But then temperature begins to play its part.
Just a little extra moisture in the air and arms start to form at the corners. A degree rise in temperature and a plate forms on one of those arms.
A 2-degree drop and tiny needles form around them. Each of these minute changes stamp their identity onto the ice. And they are so subtle that scientists aren't sure exactly why it happens.
What they do know is you end up with something like this.
A snowflake. Water in its most beautiful and complicated form.
Except I made this one. It's all my own work. Nothing at all to do with professional snow artist Simon Kemp over there, who's just out for a picnic. Well, I did the fiddly bits. I did that bit. That's mine. All my own work. The really cool thing about all of this is that every one of these shapes is different. I know it's a bit of a cliche, no two snowflakes are the same, but they're not. I guess because of this, well, infinite number of variations in temperature and humidity, every snowflake really is unique. Not just in a handful of snow or in all the snow in this giant snowflake, but all the snow that's ever fallen in the world or ever will fall.
That's because the conditions that create each snowflake are so unique that an individual shape can never be repeated. But what's really amazing is that a snowflake never stops changing. Even after it's landed, temperature continues to transform it in the most surprising ways. I'm interested to see exactly how.
So I thought I'd kill two birds with one stone. Provide a civic service for the good people of Davos by clearing this car park. Sorry. And conduct a little experiment. But it's more of an illustration, really. Yeah, we're ploughing.
First off, I need to compress the snow as hard as I can.
Manly work taking place. One last load. Right, I'm going to give it a real press this time. Come on. Yeah. I think that's about as solid as I can get that. Inevitably, the hardness of snow is something scientists have considered, and they've developed a scale associated with it. 5 stages, and it goes like this. Can you push a fist into it? No. Next down, 4 fingers. This isn't as rough and ready as it sounds, actually. The fist equates to 10 grams per square centimetre of pressure. After the 4 fingers, it's a single finger. That's 100 grams per square centimetre. No. If all of that fails, they move on. Get serious. A pen. Yeah, so it would end there, but if that doesn't work, the next scale is a knife. I haven't got a knife. I have, actually, just for the purposes of this. Yeah, I know. And then they see if the knife goes in and, oh look, it does. I haven't actually done that just because I happen to have a sword in my snowplow truck. There is a reason. This is all about the changing nature of snow, the fact that it never seems to stop altering. I've made it into this big mound and made it as firm as I can, but it's not finished there. Unless there's a sudden heat wave, by tomorrow morning, another significant change will have happened, and I may have set the locals an interesting and unexpected challenge with my sword in the snow. Mustn't forget my pen.
Overnight, the snowflakes undergo a remarkable change. All the arms and branches broke off as my snowplow crushed them up next to each other. And now they begin to fuse together in a process scientists call sintering. Joining on to each other and the blade of the sword in one rigid structure. This isn't freezing. In fact, the whole process works better when conditions are slightly warmer. It's restructuring. The next morning, we hid our cameras in a nearby shed thing and waited for the first curious locals to come past. The sword is fixed as if it's set in concrete. This isn't ice, remember. It's still snow. Snow that never stops changing. All because of temperature. When we think of temperature, we tend to think of sunshine, or lack of it. But in fact, the biggest influence that temperature has on weather is controlling the water vapor in our air, evaporating it from the ground and the oceans, freezing it into frost and snow, or condensing it into fog. I've come to one of the most predictably foggy places on the planet. The Appalachian Mountains, near Blacksburg, Virginia. Almost every morning, fog rolls up the Bluestone River and floods the valley.
This must be one of the off days. Which is why it's just as well I'm on this particular road, because here they can make their own fog at the flick of a switch.
This is the Virginia Smart Road, a 2-mile highway designed to test vehicle and traffic systems in different sorts of weather. However, we're going to use it to take a short diversion and answer a question I've often wondered about. If fog is made of water, then why isn't it clear? Why is fog white?
Do you know, I never noticed how loud fog is. It's loud, isn't it? Oh! London in Victorian times must have been deafening.
Luckily, we're not planning on doing anything with sound. We're doing it with light. Light is made up of lots of different wavelengths, each a different colour. And we see those colours when objects absorb one wavelength and reflect another. The light from this laser is scattering off the tiny particles of fog, making each one visible. But we are only projecting one colour here, green, and they're reflecting it. The air around them hasn't reflected any wavelengths, so it looks black. Project red and the droplets change colour. Same thing with violet. In fact, they reflect every colour. Add all the different ones together and they become white. Fog is just a cloud that's in contact with the ground. So the reason fog looks white is the same reason clouds look white. Because they're scattering every colour of light.
Now, you might be thinking, hold on, clouds aren't always white, sometimes they're black. Well, yes, sometimes they appear to be black, but that's mainly an optical illusion. It's your brain exaggerating any differences there are to give you what it thinks is a more useful picture. And I can demonstrate. I've cut 2 holes in this piece of cardboard. And if I put one hole over a white bit of cloud and one over what looks like a black bit, in fact, there's barely any difference. And what tiny difference there is caused by those minute water droplets fusing together to form raindrops.
The bigger drops of water make the cloud more dense. which makes it harder for sunlight to pass through. So we see dark patches that our brain exaggerates. But sometimes there's no doubt that a cloud is black. The sort of brooding storm cloud that serves as warning for one final type of weather. The type that no show on weather should be without. And it's a fitting conclusion, because it requires all three of the key ingredients that we've looked at in this series. Temperature, water, and wind in equal measure. When heat makes the ground intensely warm, and the air is heavy with water vapor, and strong winds mold the clouds, you create a lightning storm. This is one of the planet's most lightning-prone regions, Florida, USA. For most of us, the most dramatic weather we're likely to encounter is thunder and lightning. We've all heard thunder and seen lightning. But here's the interesting thing. It is actually possible to do the exact opposite, to see thunder and hear lightning. And I'm going to show you one way to hear lightning right now, without even leaving my car. Right, first of all, turn the radio on. Right. Then tune it to the AM frequency, because this works best on that. And then look for a point where you haven't got a radio station. Yeah, it's tricky. There's a lot of radio stations in the States, but here we go. There. Right, between radio stations, what we've got, well, is static. Not surprisingly, I know, but some of that static is quite important to us. Listen for those quite distinct pops. Those are lightning strikes that might be happening some distance away, but the huge electrical discharge is interfering with the radio signal. So we're listening to lightning happen. And this system is so reliable that storm chasers actually use it to track down storms. The louder the pops are, the nearer the storm is. Let me just prove to you that this is electricity making this happen. Never could do this. The static electricity I've built up on the balloon affects the radio too. See? Static. It is interesting, but no matter how effective or sometimes useful that method is, it isn't the real and actual sound of lightning. To get closer to hearing that, I need to set something up. Because static isn't the true sound of lightning, just as it isn't the real noise of a balloon. This is a very low frequency detector, and it can pick up lightning strikes from thousands of miles away. Too far away for any static to be an issue. As the planet has more than 100 lightning strikes a second, I should have a fairly good chance of hearing a few between here and the other side of the globe. What you're listening for particularly is whistles. And that is the actual sound of a lightning bolt somewhere on the planet. But if this is the real sound of lightning, then what is thunder?
I've got another balloon here. Don't ask me why, just have. Now, what happens next is no big surprise. There's a big bang. But what is surprising is where the noise comes from, because it's not the material of the balloon. If I stretch the rubber like so and pop it again, there's no noise. The noise is coming from the air.
As the balloon bursts, the air inside it explodes out, and that is a clue to how thunder works. But to find out more, I'll have to visit one of the few places in the world capable of creating full-blown thunder. They do it by firing 200,000 amps of electrical current down this narrow copper wire. Exactly the same amount as in real lightning.
So this is it. This is where it's all controlled.
Yep. So you'll need a pair of these, which is going to be quite loud.
Is it?
So you're going to be producing thunder.
Okay.
And
Right.
also, don't look directly at the arc because it's very bright.
Right, so I've come quite a long way to see something that I can't look at or listen to.
Pretty much.
Good, okay, brilliant.
Well, I suppose it is quite a lot of electricity we're playing with here.
If your kettle goes off, he's nicked your electricity to put in their capacitors. Okay, these on?
Yep.
Go. Have we started?
Yeah.
Right.
So now we can see the voltage on the capacitors.
Oh, yeah. So essentially this is going to build up a colossal charge and then discharge it.
Yep.
Dan?
Yep.
I can hear what you're saying.
Oh, yeah. Also, when the shot goes through, you might want to put your hands over the defenders as well because it's quite
Shall I
loud.
just cower under the table?
Or
I
you
mean,
could
I
cower
don't
under
mind.
the table, yeah.
Right, it's 25.
Yep, we're nearly there. Okay, so we're ready, so we can fire.
But I can't look.
Yeah, we can't
Or
look.
listen. I imagine. Oh! That, in fact, was quite staggeringly loud.
Yep.
I mean, really amazingly loud.
Yep.
So, was that thunder, or was it just sort of the discharge of the electricity leaving and arriving?
No, that was thunder.
But it didn't sound anything like thunder, it was just like that.
Yeah, and that's because the lightning arc is only 20 centimetres long here. In reality, we've got a kilometre of an arc that's all producing sound on every little bit, and it all arrives at you standing a couple of kilometres away at different times.
Because a bolt of lightning is around a kilometre long, some of it is further away from us than other bits. So parts of the sound get to us quicker, meaning that what we hear is multiple rumbles of that short, sharp bang. But it still doesn't tell us what thunder actually is. Luckily, Dan has a way to show us. Using slow motion cameras and a line of lit candles.
It's the director's birthday. We've got another 56 candles to go. We're getting there.
Once again, we return to the control room. The candles are all blown out. And if you watch carefully, you can see that they're blown out one by one. So what is going on? Well, of course, it's all to do with temperature.
A typical bolt of lightning is somewhere between 2 and 5 centimetres wide, so something close to that. These, by the way, are not for style reasons. They're for protection because effectively I'm taking a shaft of sunlight as wide as this screen and focusing it down to something roughly the size of a bolt of lightning. It is hot, but it's nothing compared with lightning. A typical bolt will reach 20,000 degrees Celsius. That's well over 3 times the temperature of the surface of the sun itself. Thankfully, it only lasts for about 1/10,000th of a second, but that's still enough for something quite amazing to happen.
Because lightning is so ferociously hot, it explodes the air around it, causing it to rush outwards, like the air in my balloon. What we see with the candles is that air moving away from the lightning bolt in a shockwave. But just how powerful is this wave? Time for another experiment. Can thunder break these glass light bulbs?
Well, I agree light bulbs are delicate, but are they delicate enough to be affected?
We think so. We certainly think that the inner ring of light bulbs will go. I'm not quite so sure about the outer ring. One way to find out.
Zap!
Yes.
They've been destroyed by the sheer force of the hot air exploding outwards. Well, except that tough one at the back. It hardly flinched. But still, pretty impressive.
I really want to see this one because I still can't believe it was strong enough.
Okay, let's have a look.
And that's a heck of a wave.
Notice, it's not the lightning destroying the light bulbs. The arc never even touches them. It's the shockwave after the flash that does the damage. Notice also that the sound of thunder happens even later, after the flash, and after the bulbs have exploded.
I mean, that is a lot of power, isn't it? A lot of energy.
Yeah, and that's just from the thunder. Like, the arc hasn't attached to the light bulb, so that's just the shockwave that's broken the light bulbs.
Which tells us how strong that shockwave can be.
But I want to see more.
What we've been looking at, impressive though it is the effect of thunder. I want to look at the thunder itself.
With very specialized cameras, we can actually attempt to capture that shockwave on screen. Not the effects, but the actual shockwave itself.
That's fantastic. That's absolutely brilliant.
That is the air exploding away from the hot lightning bolt at over 700 miles an hour.
I think we can count that one a definite success.
So there you have it. You can hear lightning. And you can see thunder. All because of the incredible temperature it gets to. We've seen how temperature drives weather. How heat gets water into the air. And cold turns it into clouds. How warmth creates winds that can bounce dust into raindrops. And tiny fluctuations in temperature shape snowflakes and frost. And it all goes to show how our weather is endlessly fascinating. A stunning display of magic and spectacle performed in front of us every single day. Even when conditions are wet and miserable, there are amazing events going on just behind the scenes. And though it may seem that only extreme weather is worthy of our attention, the weather around us every day is equally full of wonder. This is not freak weather, it's our weather, and it's astonishing.